So let's have a look at question 2. We've got citric acid in fruits. Student analysed the citric acid to determine its purity. Student dissolved a number of milligrams, 784 milligrams of citric acid in water to prepare 250 centimetres cubed of solution in a volumetric flask. Titrated 25 centimetre samples of this. Right, okay, so that's important. So the amount of citric acid that they've actually only taken a sample, 25 centimetre cubed out of the 250. So they've taken a tenth of the amount of the citric acid in a sample. Titrated it with 0.5 mole per decimeter cubed. So we've got the concentration of sodium hydroxide using phenolphthalein as an indicator. Okay, we've got the equation here, so that might be important. 1 mole of the acid reacts with 3 moles of the sodium hydroxide. Student rinsed the burette before filling it with the sodium hydroxide solution. Why the student should use sodium hydroxide to rinse the burette? Well, sodium hydroxide is going to go in the burette, so use sodium hydroxide to rinse it, otherwise the water may dilute the sodium hydroxide that's going to be in there. Student carried out several titrations, complete it. So what you do is you take the final, take away the start, and you put it there, final, take away the start, final, take away the start, final, take away the start, and you put them underneath. And you make sure they're all to 4 significant figures. All of these look as if they're to 4 significant figures. The first one is rough, so that needn't be. That's not actually to 4 significant figures at all, but the others looks as if they're starting out at least to 4 significant figures. I'm going to put them to 4 significant figures: 24.00, 23.70, 23.90, and 25.2 is just my rough one. What is meant by concordant results? Concordant results means that the results are no more than 0.1 apart from each other. So calculate the mean using 2 concordant results, any 2 that are no more than 0.1 apart from each other. So that's 1 and 3. Titer 1 and titer 3 are 0.1 apart. So I'm going to use titer 1 and titer 3 and ignore the others that are further apart than 0.1 from these 2. And so they're not concordant. So 1 and 3 are concordant. Use of titration of 1 and 3. Let's take an average: 23.90, 24.00, add them together, divide by 2, 23.95. The total uncertainty when using the burette is 0.15. So even though the burette's had 2 readings taken from it, the total uncertainty, that means that they've taken into account the fact that you've had 2 readings off the burette, is a combination of uncertainties: the start reading, the final reading, the determination of the endpoint. So everything's been taken into account. Use this to calculate the percentage uncertainty with the use of the burette. So you've got 0.15 is how far out it could be. You're using 23.95 centimetres cubed, so you divide the smaller by 0.15 divided by 23.95 and multiply by 100%. 0.63%. Use your answer to question 0.23 to find the mass in milligrams of citric acid dissolved in 25 centimetres cubed. The relative molecular mass of citric acid is 192. So what have I got? Use the answer in question 2.3. So I've got a volume of sodium hydroxide. I've got a concentration of sodium hydroxide, 0.05, and I've got a volume. That needs to be in decimeter cubed, so divide by 1,000 to turn centimeter cubed into decimeter cubed. 0.0295 decimeter cubed, and I've got 0.05 concentration. So moles, concentration equals moles divided by volume. Moles equals concentration multiplied by volume. Well, there's my concentration. There's my volume in decimeter cubed, 23.95 divided by 1,000, and that should say equals there, 0.001187. So my number of moles is 0.001187 moles of sodium hydroxide. If I refer back to my equation, I've got the number of moles of sodium hydroxide, which is this. 1 mole of the acid reacts with 3 moles of sodium hydroxide, 1 to 3. So take the number of sodium hydroxide, number of moles of sodium hydroxide, and if I divide by 3, it will give me the number of moles of the acid. So if I take that 0.001187 and divide by 3, I'll get the number of moles of acid. I need to multiply by 10, however, because I've worked out the number of moles of acid in 25 centimetre cube sample. I want to know how many are in the 250 centimetre cube sample. 25 centimetre cubes is a tenth of this amount, so I've worked out the number of moles of acid in the 25 centimetre cubed. If I multiply by 10, I'll work out the number of moles of acid in the volumetric flask at the beginning. So now I'll multiply by 10. It's 0.003992. That's the number of moles of acid that are actually in the flask. So what am I trying to find out now? Find the mass in milligrams of citric acid dissolved in there. So I've got moles. Moles equals mass divided by mR. So moles multiplied by mR equals the mass. Moles, mR 192. I think it gives you that in the question. No, it doesn't give you that in the question. You need to work it out. Oh yes, it does, 192 here. It gives you in the question here, 192 of the citric acid. So number of moles multiplied by the mR gives me the number of grams. Now it wants the number of grams, not the number of grams, it wants the number of milligrams. So if I'm turning grams into a smaller unit amount, milligrams, then I multiply by 1,000, 766 milligrams of acid. Calculate the percentage purity of sample of the acid. So this is how much I got. ,784 milligrams of impure citric acid were put in there. So I know that 784 milligrams of impure, and I've worked out from my calculations this is the mass of the acid, 766, and 784 is the amount of impure acid. So my percentage purity is the amount of acid in there divided by the amount of acid and impurities, 784, multiplied by 100% equals 97.7%.